In this unit, you will learn many different theorems and ways that you can find angle measures and side lengths of right triangles.
The Pythagorean theorem was named after the ancient Greek mathematician Pythagoras. It states that in a triangle, the short leg squared plus the long leg squared equals the hypotenuse squared. A squared plus b squared equals c squared. That's your main formula for this chapter. If you need help distinguishing the sides, the legs are perpendicular and the hypotenuse is always opposite of the right triangle. The hypotenuse is also the longest side of the triangle. Alright, so let's practice. First, set up your equation. In this example, you can plug in the side lengths to come to 5 squared plus 10 squared equals x squared. Next, square what you can. Then, add together 25 and 100. Lastly, find the square root of 125 to find x. However, the thing about this problem is that 125 isn't a perfect square, meaning its square root isn't an integer, it's a decimal. Unless it specifies to round to the nearest tenth or something, you can just simplify the radical. And now on to Pythagorean triples. Yay! Pythagorean triples are sets of 3 positive integers that satisfy the Pythagorean theorem. Basically, they're sets of 3 that will always perfectly work out when placed in the theorem. The multiples of each set also fit with the Pythagorean theorem. Moving on, the Pythagorean theorem's converse. This, being the converse of something, states the opposite of the Pythagorean theorem. If a squared plus b squared equals c squared, then it's a right triangle. Simple, right? Well, yes and no. You see, when messing around with the converse, it's actually better for you to write it as c squared equals a squared plus b squared, because if c squared is less or greater than a squared plus b squared, it's either an acute or obtuse triangle. And now for an example. Let's say a triangle had the following side lengths: 6, 7, and 8. Is this a right triangle, and if not, what is it? First, you plug this into the Pythagorean theorem. We know for a fact that 8 is the length of the hypotenuse because the hypotenuse is always the longest side. Next, we square the units. Then, we add 36 and 49. 64 does not equal 85, so this is not a right triangle. Instead, 64 is less than 35, making this triangle acute. And that's basically everything about the Pythagorean theorem.
So you have the example where you have a triangle KML where a segment or altitude MN is drawn to the hypotenuse of triangle KML. Now using theorem 7.5, we can say that the two triangles formed are similar to the original triangle and to each other. We can conclude that the triangle KML is similar to triangle MNL. So, for theorem 7.6, it says that in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two triangles. This is called the geometric mean, the geometric mean altitude theorem. So now let's do an example of that. You have the triangle ABC divided into two similar triangles by the altitude BD drawn from the right angle to the hypotenuse, where the altitude or segment BD is equal to 18 and AD is equal to 12 and CD is Y. Now let's find the value of Y. Now, based on what we know about similar triangles, we're going to make a proportion with the values given for these two triangles. So we say that 12 over 18 is equal to 18 over y. Then we're going to simplify by multiplying 12 times y, which is 12y, and 18 times 18, which is 324. Now we're going to divide both sides by 12. and that gives us y equals to 27.
Okay, so just do. Oh,
So from what we know about similar right triangles, let's do another example. You have the triangle ABC, which is divided by segment or altitude BD. We know that AB is equals to 20 and BC is equals to 15. We need to find AC and BD. Using the given values, we're going to find AC for triangle ABC with the Pythagorean theorem. We set the equation where AB squared plus BC squared equals to AC squared. Now we plug in the given values. We say that 20 squared plus 15 squared is equals to AC squared. Then we solve for the equation where 20 squared is 400 plus 15 squared is 225 equals to AC squared. That gives us 625 equals AC squared. Now we are going to simplify, and that gives us AC equals to 25. Because triangle ABD and ABCL are similar triangles, we can find AD using the geometric mean theorem. We set the proportion AB over AD equals to AC over AB. Now we plug in the values. 20 over AD equals to 25 over 20, and that gives us 25 AD equals to 400. Next, we divide both sides by 25, and AD is equals to 60. So for chapter 7.4, where we have the special right triangles, and special right triangles are triangles with some special features that can make calculations on the triangle easier to solve it. For example, a special right triangle may have angles that form a simple ratio like the 30-60-90 triangle or the 45-45-90 triangle. Theorem 7.8 or the 45-45-90 triangles theorem states that the hypotenuse is the square root of 2 times as long as each leg. This means that the hypotenuse is equals to the leg times the square root of 2. Now let's do an example of the 45-45-90 triangle. You have the special right triangle where one leg is equals to 7 and the hypotenuse is x. Now let's find x. We're going to use the 45-45-90 triangle theorem, which says that the hypotenuse is equal to the leg times the square root of 2. Then we substitute our given values, and that gives us x equals to 7 square root of 2. Theorem 7.9 or the 360-90 triangle theorem states that in a 360-90 triangle, the hypotenuse is twice as long as the shorter leg, and the longer leg is the square root of 3 times as long as the shorter leg. This means that the hypotenuse is equals to 2 shorter leg, and the longer leg is equals to the shorter leg times the square root of 3. So, for example 2, you have a 360-90 triangle where the longer leg is 9 and the shorter leg is x. In a 30-60-90 triangle, the longer leg is equals to the shorter leg times radical 3. So, to find the shorter leg, we must do the opposite. We can do 9 over radical 3. In order to simplify this, we must do 9 over radical 3 times radical 3 over radical 3. This is equals to 9 radical 3 over the radical 9, which can be simplified to 3 radical 3, and that is the length of the shorter side. We have a 30, 60, 90 triangle where the longer leg is 9, the shorter leg is 4, and the hypotenuse is x. In order to find the value of x, we must do x equals to 2 times 4, which gives us 8, and that's going to be the length of the hypotenuse.
Chapters 5 through 7 explain how you can use trigonometry to solve triangles without using the Pythagorean theorem. Trigonomic ratios are ratios that include two lengths of two sides of a triangle. The first ratio is called the tangent ratio. It measures the ratio of the opposite side over the adjacent side from an angle. As you can see, side CB is opposite angle A, and side AC is adjacent to angle A. So we can make the ratio tan of angle A equals CB over AC. In order to find the tangent of angle A, press the tan button on your calculator and put the measure of angle A in the calculator. Once you find the tan of angle A, the problem will be solved like a proportion by cross multiplying. You can do whatever tan of angle A is times AC equals CB. Now remember, this ratio only works to find a side opposite or adjacent to an angle. Now it's time for some examples. In example 1, we are given a triangle with a 32-degree angle, and the side opposite is 11, and the side adjacent is x, and we are told to solve for AC. If you put tan of 32 into your calculator, you should get that it equals around 0.625. From here, we can set up the proportion 0.625 equals 11 over x. After cross multiplying, we find that 0.625x equals 11. And after we would divide both sides by 0.625, we find that x equals 17.6. In example 2, we are given a lamppost that casts a shadow 70 degrees from the ground, and its shadow is 40 inches. And we are told to find the height of the lamppost. Your calculator should tell you that tan of 70 degrees is about 2.748. Now that we know this, our proportion will be 2.748 equals h over 40. And after cross multiplying, we find that 2.748 times 40 equals 109.92. So the height of the lamppost is 109.92 inches. The second two ratios are fairly similar. They are called the sine and cosine ratios. These two ratios use the hypotenuse of the triangle and either the opposite or adjacent sides. For sine, opposite over hypotenuse, and for cosine, adjacent over hypotenuse. For sine, the ratio is the leg opposite of angle A over the hypotenuse of the triangle ABC. So the ratio would be sine of angle A equals line BC over line AB. For cosine, the ratio is the line adjacent to angle A over the hypotenuse of triangle ABC. So the ratio would be cosine of angle A equals AC over AB. These are the buttons for sine and cosine on your calculator. Now remember, sine can only be used to find a side opposite an angle or the hypotenuse, and cosine a side adjacent to an angle or the hypotenuse. Now let's do some examples. In example 1, we know that we have to use the sine feature because we are told that the angle opposite angle A is x and the hypotenuse is 45.8. So by putting 39.1 in the calculator, we find that sine of 39.1 is 0.631. After this, we can solve the problem by using the same method as the tangent ratio. We can set up a proportion 0.631 equals x over 45.8. So opposite over hypotenuse. And after cross multiplying, we find that x equals 28.88. In example 2, we know that we have to use cosine because we are given a side that is adjacent to an angle, and we are told to solve for the hypotenuse, which is x. Now we can find cosine of 60.3, and that is equal to 0.495. Now that we know that cosine of 60.3 is 0.495, we can set up the proportion 18.54 over x equals 0.495. And after cross multiplying, we find that 0.495x equals 18.4. So then x would be equal to 37.45. In addition to finding side lengths, we are also able to find the measure of angles by using the inverse of trigonomic ratios. For example, if we are given triangle ABC and we are told to find angle B, we can press second sine on our calculator and put the ratio of the line opposite over the hypotenuse of angle B. So our ratio can become inverse of sine AC over AB equals the measure of angle B.
Oh my god. This is either so like uncomfortable as that is not funny. Because it's funny. I thought it was funny when I was doing it, and then watching it, I was like, this is just making me feel very uncomfortable.
Wait, what is it?
The video I did. Because like I'm trying to be funny, and it's like me and funny like.
Where is it?
So that was good. I wanted to zoom. Oh, there
Yeah. Do you know how to make it not zoom? Yeah.
Yeah.
Is that
Wait, I'm just doing that. This picture?
Or not?
Bigger
Did you
picture?
figure it out?
No, because it always cut off.
Yeah, but like it wasn't like that.
Oh.
You go to the little rock.
Yeah.
That's really your background. Yeah, dude. And then you can say crop.
It's fit. So it doesn't
Where's your script?
It's at the eight.
And I did some of
Yeah, I
6.6.
And then I can just okay, so all done. So approximately
I think the reason why your script is so short is because it doesn't really go over
That's,
think
we're
if
gonna do that in video.
also if
That's
we
how we
if
probably-
like if
okay, but he's writing the script,
or like
and I think he wants that to be.
One second.
I can
So I don't really care about it.
I might sound a little weird, but
Oh, there's like a massive. I think it's because Alex is
oh my god, I wasn't even recording.
Oh my god.
This can also be done using the inverse of the cosine or tan ratios. Now let's try an example. In this example, we are told to find the measure of angle A. We know that we have to use the inverse of tan because we are given a side length opposite and adjacent to angle A. Now we can put second tan in our calculator and then do the ratio of opposite over adjacent sides, so 15 over 20. And we find that that is 36.87. So now that we know that the inverse of tan of 15 over 20 is 36.87, we know that the measure of angle A is 36.87. In example 2, we know that the hypotenuse is 16.1 and the side adjacent is 13.5, and we should find the angle in between those two sides, so we know that we should use cosine because it's adjacent over hypotenuse. So if we put second cosine on our calculator and do 13.5 over 16.1, we should get that the angle measure is 33.03. So now that we know that inverse cosine of 13.5 over 16.1 is 33.02, we know that the measure of angle A is 33.02 degrees. Now you can solve a right triangle. This can be done by using all the different theorems learned in this unit to find the side lengths and angle measures of a right triangle. In this example, we are told to find the length of AB, CB, and the measure of angle B. First, in order to find angle B, we can use the triangle sum theorem. So we can do 42 plus 90 plus B equals 180. And then 42 plus 90 is 132, so 132 plus B equals 180. And 180 minus 132 is 48, so the measure of angle B is 48 degrees. Now we can use the tangent ratio to find the measure of BC. If we put tan of 48 in the calculator, we can find that it is equal to 1.11. So now our proportion will become 1.11 equals 70 over CB. And after cross multiplying, we have 1.11 CB equals 70, and after dividing, CB equals 63.06. Finally, we can use cosine to find the measure of AB. If we put cosine of 42 in our calculator, we find that it is 0.743. Now that we know this, our ratio will become 0.743 equals 70 over AB. And after cross multiplying, 0.743 AB equals 70. So AB equals around 94. In example 2, we are told to find the measure of angle C, the measure of line BC, and the measure of line AB. First, let's find the measure of BC. We know that we have to use the sine ratio because we are given an angle and we have to find the side opposite it, and we have the hypotenuse of the triangle, which is radical 10. So, now that we know we have to use sine, our ratio will become sine of 57.8 equals BC over radical 10. So putting sine of 57.8 in our calculator, we find that it is 0.85. So it becomes 0.85 equals BC over radical 10. And 0.85 times radical 10 equals 2.7. So BC is equal to 2.7. Now let's find the measure of AB. We know that we have to use cosine because we have the hypotenuse of the triangle and we need to find the measure of a line adjacent to the angle, A. So now our ratio for cosine will become cosine of 57.8 equals AB over radical 10. And cosine of 57.8 in the calculator is 0.532. So now that we know that cosine of 57.8 is 0.53, we can set up the equation 0.53 equals AB over radical 10. And 0.53 times radical 10 equals 1.7. Now, let's find the measure of angle C. We have the line opposite and adjacent to it, so we know that we have to use the inverse of tan. So we can make the equation measure of angle C equals inverse of tan 1.7 over 2.7. Once we put inverse of tan 1.7 over 2.7 in our calculator, we find that it is 32.2. So now that we know that inverse of tan of 1.7 over 2.7 is equal to 32.2, we know that the measure of angle C is 32.2. Now you can solve right triangles using the Pythagorean theorem, figure out if it's an acute, obtuse, or right triangle using the converse of the Pythagorean theorem, use similar triangles to find out if the triangles are similar, solve 30, 60, 90 triangles, solve 45, 45, 90 triangles, use the tangent, sine, and cosine ratios to find side lengths, use the inverse of tan, cosine, and sine ratios to find angle measures, and you can solve right triangles using all of these theorems.